In this video, I want to start having a look at locus. So a locus can be thought of in two different ways. It can be thought of as a set of points that obey certain conditions, or we can think about the path that's traced out by a single point that's moving, but it's still guided by those conditions that are set. There's two ways that we can describe a locus. We can either describe it geometrically or algebraically. So in this video, we're going to have a look at how we can switch between the two of them. So before we start doing that though, I want to have a look at some of the more common loci or locuses that we see. So if we've got the set of all points that are the same distance, so we'll call that distance r, from a given point that we're going to call C, then that locus is a circle that's centered at C with radius r. The next one is if we have 2 points, A and B, and we want the locus of all points that are equidistant, so the same distance from A as they are from B, then that's going to be the perpendicular bisector of the segment AB. So the last one's a curve that we see quite often in the mathematics course. It's a parabola. So a parabola is a locus of a point whose distance from a set point and a set line is equal. If we have a look at a few examples, this first one asks us to sketch the locus of the point that is 5 units to the left of the y-axis. So it's that path that point's going to trace out if it is always 5 units to the left of the y-axis. Then it asks us to use the graph to write the equation of the locus. So we're going to sketch that graph. Again, you guys should always be using a ruler for these sorts of things, because otherwise it comes out really dodgy like that one just was. But I can't on this. So your graph should be much neater than mine are. So that's our x and our y axes. Now, if we've got a point that's always 5 units to the left of the y-axis, so our y-axis is here, 5 units to the left would be over here at -5. So we want the locus that the path that point is going to travel if it's always 5 units to the left. So if we've got this line here, every point on that line is 5 units to the left of that y-axis. So we can use that then to write the equation of that red line, which would just be x is equal to -5, because every point on that line has an x coordinate of -5. So our second example asks us to complete the square and find the centre and the radius of the circle with equation x squared plus 6x plus y squared minus 8y equals 10. So we're going to rewrite this, and we're going to have to complete the square on each section. So on these x terms here, we're going to complete the square. And on these y terms here, we're going to have to complete the square. So when we rewrite it, I'm just going to leave some gaps in there. So x squared plus 6x plus y squared minus 8y is equal to 10. So completing the square, we need to figure out which numbers we need to add to these to make each section a perfect square. So with this one, we're going to halve the coefficient of x. So half of 6 is 3. And then we're going to add that 3 squared. So we're going to add 9. You can write it as 3 squared as well if you want to. But if we're adding 9 here, then we also have to add 9 to the other side of that equation to keep it balanced. In this one then, half of 8 is 4, so we're going to add 4 squared, which is 16. So add 16 to the other side as well. So now we can factorise both of those sections. So this one here would become x plus 3 squared, because this now is a perfect square. Plus, now this one's going to be y minus 4 squared, and that's that minus because there was a negative here in front of that y term. And that's going to be equal to 35. And now we can read it off. So this now is looking like the equation of a circle. So our equation of a circle with centre, hk, and radius r looks like x minus h squared plus y minus k squared plus r, equals r squared. So we can look at that general form of a circle and look at our equation that we've got, and we can say that the centre is going to be -3 because it was minus h, but ours is positive, so it's going to be -3, 4. So centre at -3, 4, and the radius is going to be equal to the square root of 35. Our last example asks us to find the equation of the locus of the point P, which has coordinates x, y, that's equidistant from the points A and B. So because we're thinking equidistant, we need to be thinking about the distance formula. So we can calculate the distance between A and P and make sure that's equal to the distance between B and P. So our distance formula, if we've got the coordinates of 2 points, would be x2 minus x1 all squared plus y2 minus y1 all squared. So we want, if it's going to be equidistant, we want AP to be equal to BP. So we can use the coordinates of this point and put them in our formula, but it's going to be a little bit easier if we think about all of this without the square root sign. So what we're actually going to look at is AP squared has to be equal to BP squared. So if these two things are equal, then if we square them both, they still have to be equal. And that just means that we can look at this distance formula without that square root sign over the top of it. So if we substitute in our values now, if we do AP first, so we're going to go x minus minus 1. So we'd have x plus 1 squared plus, and then we've got y minus 3 squared. And that's going to be equal to BP squared. So we're going to have x minus 5 squared plus y minus 1 squared. And now we're going to expand all this out, bring everything over one side and find our final answer in its simplest form. So expanding this one out, we would have x squared plus 2x plus 1. So don't forget that when you're expanding something like that, you are going to end up with 3 terms. Then expanding this one, we'd have y squared minus 6y plus 9. And that's going to be equal to x squared minus 10x plus 25 plus y squared minus 2y plus 1. So now this is looking like a pretty huge mess, but if we try and bring it all over to one side of that equal sign, it's going to be a lot neater. So if we bring all of these terms over to the left-hand side of our equation, we'd subtract x squared. So x squared minus x squared will just leave us with 0, so those cancel out. Same with our y squareds, we've got a y squared here, and we're going to minus y squared, so those will cancel out as well. Before we do anything else, I'm just going to simplify a little bit. So we're going to have 2x minus 6y, and we've got this 1 and 9, so plus 10. That's going to be equal to minus 10x minus 2y, and we've got this 25 plus 1, so we've got plus 26. That just makes it a little bit nicer and neater to see. So if we add 10x to both sides, we're going to have 12x. If we add 2y to both sides, we'll have minus 4y. And if we add 26 to both sides, to subtract 26 from both sides, we'll have minus 16. So that's equal to 0 now. And the last little thing we can do is we can simplify that down because they all have a common factor of 4. We can divide through by 4. So we'll end up with 3x minus y minus 4 is equal to 0. So that's the equation of all the points that are equidistant from A and B.